What did we say 2 arrows meant?
2 reagents or 2 reactions.
That is not at all what we said it meant. Anybody else? What did we say 2 arrows meant? Exactly what he said. It just means a synthesis, not one step. That's it. It could be 2 steps, but it does not mean that. It's just saying you have to do more than one. That's all it is trying to say.
So what about the ones that have like 3 arrows? Is it the same thing?
It's the same thing.
Okay.
So it's just a default notation on however somebody put it together or drew it. Sometimes they draw it as 2, sometimes they draw it as 3. It's an artifact of whoever's writing the question. So, first place you should start would be identifying the chemistry. So where do we see chemistry in either reactant or product? I don't care. Okay. Pi bond is useful to label as chemistry, but I would take that a step further than just the pi bond and reference also the carbons that are reactive. So when we're talking about that pi bond, we're also saying we have a blue carbon that's reactive. We'll call it a purple carbon that's reactive. Okay, in our reactant. In our product, we still have a pi bond, but where is that pi bond now located?
Blue carbon.
Say again?
All the blue carbon.
Blue carbon still. So nothing happened? We don't do any reagents because it's... So again, this is why it's important to reference the carbons. So yes, the blue carbon is reactive and we have another carbon. We can call it the orange carbon. So if we're going through and looking at the chemistry at the blue position effectively doesn't change. The chemistry at the purple position goes away entirely, and chemistry appears at the orange position. Okay? One of the things that I would like you to kind of see is through the course of this reaction, our chemistry is kind of moving up and out. Okay? So if we were to do like a synthesis system with those cards, we'd be selecting cards where the chemistry is moving through that purple, blue, and orange spots. We would not be expecting to see any chemistry show up at any of those other carbons because those other carbons didn't change in the course of this reaction. So we could use the matching cards to kind of help us think through this process and slowly piecewise through it. Kind of make sense? Okay. What changes occurred?
Orange carbon becomes a sp2 instead of sp3.
I do like that. That is not where I expect you to go, though. So you went to more towards the raw internal chemistry, which is good. Yeah, let's go with that. Let's go with our big picture stuff first. Okay? So our big picture is that our pi bond has moved. I should have said moved, not bond again. Is there a chemical reaction that allows the pi bond to move? No. Okay? So when we go through and evaluate this, we have to now shift back from that pi bond moved as the big broad strokes and start to get more refined within that system. Okay? Within that, you could zero in on that orange carbon going from sp3 to sp2. I would argue you've zoomed in too far. Okay? Because we're still looking at what are the reactions that do that. And if we talk about what reaction makes an sp3 go to an sp2, that could hit some weird gray area. Like we're going to get a lot of, or not a lot, but several reactions that could potentially be doing that and make that a little bit more challenging to nuance. So what we're trying to fit within this is the context of what our reaction types are. So what are our reaction types?
Like SN2.
SN2 would be an example of a mechanism for a particular reaction. What's the reaction?
Substitution.
So we could go with, we're just going to do it in no order. Substitution. Say again?
Elimination.
What else?
Replace. Radical.
And radical's gross, and I'll add some more information on the radical in a second. And the last one? Addition. For us to really do any kind of synthesis questions, we have to have substitution, elimination, and addition. Those are pretty much prerequisite reactions to allow us to do any kind of real synthesis system. Okay? And arguably what we've done here really isn't that much of a synthesis. It is moving the functional group around, but it's pretty simple. And even with that, we needed those three reactions. Right? So within that context, we want to now go back and say, well, what things changed? Yes, the pi bond moved. None of our reactions allow us to do that. So let's zero in a little bit closer. What had to happen to the pi bond in the reactant? It had to break. I'll color that differently. So our red pi bond, I keep writing bond. God, it's killing me. The pi bond broke. What else happened? Our pi bond formed. Right? And this is where color coding can come in handy. This is one of the reasons why I gave you the colorful pen, because you could potentially color these things out. Yes, we have more than the 4 colors. Okay? So within those two pieces of information, do we know reaction types would allow us to do those systems? So, and either focus, breaking the pi bond or forming the pi bond. What reaction type would allow us to do either of those two systems? Say again?
Elimination.
And elimination does what?
As 2 sigma.
Okay? And elimination and addition are always confusing to deal with, which is why we need to nail those down pretty quickly here. Okay? So, what is the difference?
Elimination adds a pi bond?
The elimination is loss of 2 sigma. There's the elimination with the formation of the pi bond. Okay? Which means we're talking about that second step. So what reaction is a pi bond breaking? That's our addition. With those 2 categories narrowed down, that can help us kind of reason through some of these options. Okay? And we've got either going from our reactant in an addition system to a new product, or we could look at the product of some unknown reactant. Either one of those focuses is perfectly fine and acceptable because it's helping to bridge the gap between those 2 molecules. Okay? How do you decide which one to do?
Your own discretion.
It is perfectly, well, so it is your discretion. What are you relying on to help you understand which one you're going to choose? And yeah, it's your discretion, but what are you using as your discretion? And for the record, this could be different for everybody.
Let's start with the reactant.
Okay? A lot of people want to start with the reactant, which is perfectly acceptable. Okay? For me, what I would focus on is instead of I am used to going from reactants to products, I would think more about the reactions themselves. Which reaction are you more comfortable with? Additions or eliminations?
Addition.
Okay. And if you're more comfortable with addition, that's fine. You can now zero in on what things you need to do an addition. So to do an addition reaction, what things are we trying to do?
Create 2 sigma.
Okay. I need to form 2 sigma, and I need to break the pi bond. That says beak, but close enough. There's an R in there. It's just invisible, like a silent R, it's an invisible R. Okay? I would actually lean out with the pi bonds and say, I don't even have to worry about breaking the pi bond. Okay? Because I could switch this instead of being a reaction arrow to a resonance arrow, and this could help give me an understanding of the chemistry of that carbon. Okay? Is that a good resonance structure?
No.
No, that was supposed to be a good one, but I screwed it up. Okay? This is why you draw it out and you can get more comfortable with it. Okay? Why is it bad?
Because the carbocation should be on the most substituted position.
Okay? More than likely, we would expect the carbocation to be at the more substituted position. We should have the positive charge there, the negative charge there. This now gives us some context of chemistry, okay, for this particular system. We can even still color code the atoms. Purple. Which of those two positions do you want to look at? Blue or red?
Red.
Okay.
Wait.
Sorry, purple.
Blue. Sorry.
Blue or
I
purple?
said red.
I asked it wrong. Okay, and it's fine to say blue. And ultimately, again, it doesn't matter. We can pick either one. Okay. Does everybody want to look at blue?
Sure.
You kind of shrugged. Why?
Because it kind of the way that I was to form a reaction from that, but it's not what we want to.
But that's where the chemistry is going. Right?
That's true. That's where the chemistry is going. Which means ultimately, is that chemistry necessarily changing?
Yeah. I mean,
But the blue is not changing.
The blue is not changing. Okay? It's not wrong to look there by any stretch of the imagination, but ultimately the blue isn't really changing. So let's focus on the part that we know needs to change. Then we can layer in the part that doesn't change. Kind of, sort of? Okay. Again, that's just my flow. That doesn't have to be the way we go at it. So what happens to the purple carbon?
It loses electrons.
it stabilizes.
Technically, it doesn't lose electrons.
Or donate them.
Okay, so we could go with that. That's a little bit better. It's going to donate electrons. What is it donating electrons to?
Hydrogen.
Getting to the larger picture of what changed, if we look at that purple carbon, it has one hydrogen in the reactant, and it has 2 in the product. So if we're looking at those bigger picture changes, what's happened there is that that negative carbon has to react with a hydrogen, and that hydrogen is likely what charge?
Positive.
Why does it need to be positive?
To stabilize the negative.
Awesome. Okay. So somehow or another, we need to get a reagent in here that's positive. Okay. Cool. We could now shift our focus to the blue spot. Okay. Because I can't just put on the hydrogen and then say, oh, I'm at the end. I just add H plus and I get this structure. Okay. And there's a couple reasons for that. Number one, H plus is not a reagent. Okay. We float real fast and loose with using H plus. Okay, we'll almost always just say, oh, we're going to add H plus to the system, and we don't really stress about the source. When we're doing synthesis, you have to add an actual chemical reagent. The end of that chemical reaction must end at a chemical product. These are both charged. Neither of them are reagents nor products. Okay, so if we want to use H plus, we'd have to use a counter ion. Okay, something to counterbalance this. That doesn't mean, oh, I just add H2O. Now it's H3O plus. You shifted the problem to a larger structure. It's still positively charged.
Why couldn't you add H3O plus?
If we, and so again, if we do H3O plus, it's still positively charged. That's not a reagent. I can't go into the stockroom and say, give me H3O plus, because they can't. It doesn't exist. Where does H3O plus come from? What reaction? And for the record, it's not on the board. Well, I would need a source of H plus and
Oxygen.
Water.
water. I take a source of H plus and I mix it with water. So when I'm saying H3O plus, I want something that gives me H plus, yes, but it has to have a counter ion that doesn't do anything else. Can that counter ion be chloride?
Yeah. Hydrochloric acid.
Cool. That is absolutely true, hydrochloric acid, and that will generate H+. What else does it generate? Cl-. And what can Cl- do? It can act as a nucleophile, right? Which may be a good thing, separate issue. If we're just talking about all I want is H+ or H3O+, that's a bad thing because that's adding chloride. I don't want chloride ion. So if we're just adding H+, we're adding that H+ with the counter ion of something that is incredibly stable. Sulfuric acid, phosphoric acid, nitric acid. All of those, the counter ion is resonance stabilized, effectively neutralizing its ability to act as a nucleophile. Okay? Which will play a role in many reactions we do in the lab. Okay? So do I want just H+? Okay, fine, let's just say, okay, we somehow got it, H3O+. I still end with a positive structure here. That's not an ending point. I can't add another reagent because this isn't done. And if I added H3O+, what else is floating around? H2O. And what would the H2O do? It would donate its electrons to that. And where we would end it would be a positive oxygen, still not stable, so now what happens? Let's go of the hydrogen is a good kind of answer. It can steal the electrons back from our hydrogen. And we would end now with a final structure of the alcohol. Right? Do I want the alcohol? No. Okay, so what does that mean? We said H3O+, but H3O+ puts an alcohol on. Do I want H3O+? No. And here's the frustrating thing. What does that mean about all this lovely work that we drew down here that was all correct and lovely?
It's worthless.
It's worthless. Right? So while H3O+ is a sort of possibility by adding a super strong acid, okay, with a non-nucleophilic counterion, H2SO4 and water, that doesn't get us to a spot that we want. Okay? We still have to stabilize that positive.
Well, wouldn't we need to deprotonate the carbon the opposite end of that?
Awesome. What you're projecting is at the next stage, I want to remove a hydrogen from that position so that I can make my pi bond, so I can start the elimination. That's great, except I'm not at a point where I can do that because this reaction isn't done. I don't have this molecule. It doesn't exist. This is stalled in my synthesis. As far as a reaction goes, what have we done in the lab? Absolutely nothing. Because we don't have H+. We vaguely said, okay, maybe we can do H3O+, and H3O+ doesn't work. What reagent do I add to this? What do I want it positioned at that carbocation, which I guess we were calling blue?
Electrons? I mean, it's possibly charged, therefore it wants electrons.
Yeah.
You'd want a good leaving group there. I don't know.
Okay, that's where I want to go. So let's walk through what we've done here. Our beaking the pi bond, we decided didn't really matter, and we just needed to form the 2 sigma. We've formed one of them, our hydrogen. To finish the addition reaction, I need to know what that other sigma is. Okay, and at this point, we're like, I don't know what to put. Okay, but what you're suggesting, Anthony, has to do with what we know about the elimination reaction. What has to happen in the elimination reaction? Formation of the pi bond. And if the breaking of the pi bond wasn't a big deal, what do you think about the formation of the pi bond? Equally not going to be a big deal. Right? It's not a bad thing. Whoops, form should be positive there. But our primary focus on how we make the pi bond has to do with the other things that are happening in the elimination. What are the other things happening in the elimination?
Getting rid of 2 sigma.
The loss of 2 sigma. What are the 2 sigma that are lost in an elimination reaction?
One on each end of the pi bond.
True. One of them is a hydrogen. Okay? So we're talking about removing a hydrogen from the orange position. So that's a carbon-hydrogen bond. Is that an easy bond to break?
No.
No, that's a hard bond to break. We're talking about a non-polar covalent bond that's not likely to break. Okay? And if that's our hinge, is that we have to break the hydrogen sigma bond, it's useless. Nothing's going to happen. But elimination does happen. So there's another sigma bond that breaks. What is that other sigma bond to? You've used the word, Anthony, by the way. There's a leaving group. When we talk about the basic components for these reactions, this is one of the reasons why in OChem 1 we talk about those pieces so that we can identify them, particularly when we move to synthesis. I need a loss of a leaving group. If I go back to my stalled out reaction where I'm like, I don't know what to do I have the hydrogen that I could remove in my elimination?
You have the hydrogen.
I do have the hydrogen. Do I have the leaving group?
No.
No. So maybe what I should do with this H plus is make sure that I also add something that could act as a leaving group.
Bromine.
What if I put on Br minus? So not bromine, bromide. Okay? The H plus reacts with our negative, goes on to our structure. The bromide can then react with the positive. What happens? Do I now have a neutral structure?
Yeah.
Now that I have a neutral structure, what could I do?
Elimination.
Isolate it from all the other junk, and then run my elimination reaction. To run the elimination reaction, what has to happen? I have to lose a leaving group. Do I have a good leaving group?
Yes.
Hell yeah, awesome. That could be on its way. Okay? But then I have to break that sigma hydrogen bond. What did we say about how easy it was to do that? It's not easy. So what might we do to help break this?
The base.
Why do I want to use a base? How do you know it's H plus that's coming off of this?
Well, would we need a big bulky base?
We're getting into the specifics of the base. I'm not even asking that. Why do I even need a base? Why is this H plus and not H minus?
Because electrons with pi bond need to come from somewhere.
How do you know the electrons have to come from that bond and not from the carbon-bromine bond?
Does bases donate electrons?
Bromine is more electronegative. So what you've done is propagated this system out. That's a partial negative bromine, which makes the carbon partially positive. Okay? The hydrogen is partially positive. That carbon is partially negative. To make the pi bond, what has to happen? Negative shares with the positive. But for that negative to be there, I have to remove that H plus. Okay? So the hydrogen is popping off as an H plus. That's an acid. What reacts with acids? Bases. So what do I need as a reagent is a base. Just writing base is generic to a synthesis. We need to be as specific as possible. That's not particularly specific. Okay? That would get you some points because you're showing you understand it, but now you're missing some of that reagent knowledge. Okay? So you could go through and list the best base you can think of. Hydroxide. Is hydroxide a base? Yes. Is that charged? Yeah, so we go, well, it's sodium hydroxide. I get it. Okay. Still, negative hydroxide. Does that reagent work?
No.
Why not?
Because it can react with any hydrogen off any of the carbons.
Because that base is so small, it's got a variety of different options that it can do. It could act as a nucleophile. Sterically hindered, we don't stress about that. But it's also going to react with any alpha hydrogen. Okay? Where our leaving group comes off, we can pull from any of those hydrogens. And if we pull from our red carbon structure instead of that orange hydrogen, what happens is we go backwards. So I need to choose a base that has a harder time getting into those red carbons, and it has an easier time getting into that orange carbon. Okay? And this becomes one of the issues within how we draw structures, is it's not inherently obvious the difference between those. Okay? But there is a steric hindrance. There's more electron bulk around the red positions than there are around the orange positions. So if I use a really big bulky base, that bulk can't get in to react with the red hydrogens. And instead, it will selectively attack the orange positions. Which means I want a bulky base, which means sodium hydroxide's out, and instead I bring in
Butoxide.
T-butoxide.
What is the, this may be a dumb question, but what is the T in butoxide?
T stands for church, which is why I was actually going to draw it all out. Okay, we still got, and I'll come back to that in a second. We've got the negative charge. Again, those have to be stabilized, so use any metal you want. Sodium is the easiest. You could drop a sodium on there and we're okay. Okay. What does the T in T-butoxide stand for? That T is a lowercase t. It represents that carbon in our structure. Okay. Let's look at this. It's bute, right? What does bute mean? 4 carbons where?
The chain?
In the chain. Do you have a 4-carbon chain? No, you have a 3-carbon chain. Well, why are they calling it bute? Okay. This is a common name approach, unfortunately. And what they're saying is you can take 4 carbons, and when you arrange them together in this particular configuration, there's one way that you produce a carbon that is tertiary. A carbon connected to 3 other carbons. So when we say T-butoxide, that's T for tertiary. Arrange the 4 carbons to make that true. Only way to do that is to create this shape. Kind of, sort of? Okay. That allows you to draw that last step. Okay. That's a lot, don't do that. That's a lot of work. We happy with it all? At least as happy as we can be? Okay, because I'm about to delete it all. Okay. Oops, I didn't want to edit or completely close out. What you're expected to see as a reaction is this, or produce. That's the answer. And that becomes one of the frustrating things, at least from my perspective, both as a student and as an instructor. Because as a student, we look at it, well, how the hell did you do all that? Remember all that writing I had up there? I did that all in my head. Okay? And as a student, that's just obnoxious. Okay? As an instructor, I find it obnoxious too, because I'm like, how do I tell people that that's how you're supposed to do it? What's the lesson? I just need to memorize that it does this. And that's the wrong lesson to get out of OChem. You shouldn't just be memorizing things to get out. What you should be doing is memorizing how things work and the process behind how you navigate it so that you can apply that knowledge elsewhere. Kind of, sort of? But when you look up synthesis, this is what you're going to see. This is the answer. Okay? What would I expect to see on your paper? Mostly what I had written up there before, and all I'm looking for is HBr and T-butoxide A. That's it. So all of that work boils down to those 2 really simple statements. And as long as they're there, I move on. Okay? Which again, if I was a student, I'd be pretty frustrated by that. As an instructor, I'm pretty frustrated by it too. Because you write all this BS on the paper, and I just look for 2 things and I'm done and move on. Like, I'm not giving you really any credit for the amount of effort you put into that. That's a little rude. Make sense? Okay. 2, synthesis. It is a challenging thing. I would highly encourage you to do more synthesis as practice, because what it's going to help you to do, hopefully, is see more and more reagents and start that memorization process, okay? That isn't just rote memorization, it's applying what you're trying to memorize. It's the frustration of finding those pieces, and that's going to help it stick in your brain so that you can answer other questions other than synthesis. Okay? A huge part of synthesis, and if anybody ever watched these lectures that had any pseudo power over me, would probably get a bit upset, because if we look at the point values for this, I'm giving you 4 points for all of that work. That's next to nothing. What do you think my expectation is of you?
To write out all your work.
That's 4 points out of a 100 point exam. Do you really expect me to think that you're going to write all that work out? No, what's my expectation of you? You're going to skip it. Okay? It isn't worth the point value. It isn't worth the trouble to go through and do that. Where it's worth it is in the practice and the homework and all of that. Okay? That's where it's important. On the exam, it's a relatively minor point. I can use that to help differentiate students that really know what's going on versus students that maybe know most of it. That's about all I can use it for. I don't think it's worth the effort to make an entire test out of synthesis, though I've seen plenty of exams like that. Synthesis is supposed to be the aspect of OChem 2. I think that's dumb. Okay? Kind of, sort of? Okay. Next. Sure, you can. You got whiteboards. Split it up, 2 groups. Before we move on to the next question, this is just for the people at home. We were looking at this particular synthesis and trying to figure out the reagents that would allow us to navigate it. And then this is the thought process that students went through to try and get to that final answer. After we address that, we've then been requested to take a look at a new reaction. For those of you that were curious and wanted to look at that answer, that shows up about 31 in the video. Right, just that final answer. So we've got a energy diagram question. It would be nice if I had a little bit more space here, but I think that's all I'm going to get. Okay, so we're looking at an overall reaction, and we're being asked to label our 2 products as kinetic or thermodynamic. Okay, what does kinetic mean? Okay, I did hear you. I was just doing some more work. So kinetic is about speed. What is thermodynamics about?
Stability.
I want to color code differently. Kinetics is blue because it's fast.
I associate blue with speed.
No, I suppose to associate red with heat for thermodynamics. Is really what it comes down to. So thermodynamics, did you say energy of the products?
Sure.
Okay. I got too lost in my color coding. Okay, so that's the energy of our products. So if we're going through and comparing these things, we're trying to figure out, I know it says SPED, what's going on within these. If we were to look at an energy diagram, so an energy diagram, we've got energy on the y-axis, and then we usually have what's known as the reaction coordinate on the x-axis. What we're saying is as we progress further to the right, we're becoming products. Okay. So if we were to put both our kinetic product and our thermodynamic product on this kind of diagram, okay, if we're talking about speed, what does that mean?
Lower activation energy.
Activation energy. The activation energy is the difference between our reactant energy and our transition state. Okay, so if we were to look at the thermodynamic, we might be saying its transition state is higher. Okay, that's all kinetics is looking at. Okay, and if I get a little bit more precise, we should actually even erase the downhill part of that. It's just the peak. Okay, so in the case of the blue one, our kinetic is a smaller activation barrier. It's going to happen faster. If we shift our focus and now look at the energy of the products, okay, and we're going to talk about a thermodynamic product, what are we concerned about?
Lower energy product.
We'll call this kinetics. New diagram. We're now saying that the energy of our reactant and the energy of our product, the product is lower in energy. Okay? Whereas if we had the reactant in the same spot, the product of our blue one would be higher in energy. Okay, so we'd call that red one the thermodynamic. Can we say the blue one is kinetic in this new energy diagram?
No.
No, why not?
Because it only focuses on the activation energy.
Okay. Kinetics is all about the activation energy. Thermodynamics is all about reactant versus product. So if we look at the second energy diagram that we've drawn, we haven't specified an activation barrier. So we have no information about what is kinetic. All we know is thermodynamic. Does that make sense? Typically, when we think about or discuss our kinetic versus thermodynamic, we're just going to call that one thermo. What we're looking at for energy diagrams, let's see if I can actually draw this correctly, fast, is something like this. That was a bit ugly, but it's close enough. What we're trying to point out is that there's a crossover between those two curves. Okay? When we talk about kinetic and thermodynamic, that's what's happening. That's the big deal. Okay? Do all reactions have this crossover?
No.
No. Because we could very well have systems, and now we'll just call them red and blue, where we get something like this.
Well, it's across the beginning.
If we look at the red one, does that one happen faster or slower? Faster. So that product would be kinetic. If we look at the product energies, the red one is also lower, so it's also thermodynamic. So the kinetic and thermodynamic are really only referencing different parts of the energy diagram. Every reaction is going to have different types of energy curves. Okay? So it all depends on those individual systems on whether we get a crossover or not, right? And what labels as what. That kind of makes sense? Okay.
So something could be both the kinetic and the thermodynamic when it comes
Yes.
to-
And if it's both the kinetic and the thermodynamic, what does that ultimately mean?
It's the right.
It's the only product, okay? Because it is both fastest to form and the most stable. That means it's the only thing I get, okay? That's our ideal scenario. Arguably, most of OChem 1 is that. We only really talk about one product. We aren't concerned about multiple products. As we move into OChem 2, we start to hit this gray area of kinetic versus thermodynamic, and that now becomes a larger role and plays a very critical role in how our individual reactions run. Okay, so we pretty much have to be constantly aware of this. Where it first appears is in our electrophile addition. And if we start with a diene and HBr, we would talk about how it reacts. Okay? The most reactive thing in our reactants is what?
The pi bond.
Pi bond is a good answer, a wrong answer. Can you name that pi bond structure?
Conjugated?
1,3-butadiene. I pour 1,3-butadiene on you. Okay, I don't know anything about it. Okay, fair enough. Can you name HBr?
Hydrobromic acid.
Hydrobromic acid. I pour hydrobromic acid on you.
Ow.
Ow, okay, there's a difference in response. Why is there a difference in response?
Acid.
One is reactive and more reactive. There's my primary focus. Okay? Since I know HBr is an acid, okay, and a step further that we should have been told to memorize in Gen Chem, whether we were or not, is a strong acid. Okay? When I look at the reactivity here, what I should be seeing is I have H plus, the alkene, and Br minus. So my primary focus is now I have this H plus. That hydrogen is missing its octet. It needs electrons. So now what must I find? Electrons. And where do I find said electrons?
In the pi.
Now I can go to the pi bond. Okay? So, and you're not wrong by saying the pi bond. You're just thinking of the starting structure. That may be where you find the chemistry. It may also not be. So broaden your horizons a little bit and recognize that you should be looking at the arrow and your starting material to think about chemistry in both those spots. Okay? So cool. Is there a difference in the pi bonds?
No.
Nope, which means I can pick any pi bond I want, and I'm going to have it react. So I'm going to take the electrons in that pi bond, and I'm going to share them with the H+. Formally, we don't, depending on how you want to nuance this, maybe we decide that we don't actually have that positive and negative yet, and that we would have to have the electrons kick. I don't particularly care. I'm not going to take off points on something like that on an exam, okay? But it's something that we can consider when drawing this out. We reacted that pi bond, which means our hydrogen now needs to be connected to our structure. Where do we connect the hydrogen to the structure?
At the very right end.
Blue or red?
Red.
Red, okay? Why do you want to place that hydrogen at the red position?
Because that's where the negative charge would be.
Okay, so what you've done is you looked at that starting material and recognized internally in your head that it is more stable to put the negative on the terminal end and the positive on the inside. Okay, phenomenal. Yes, that should be something you are doing in your head to predict where this chemistry is coming from. I just realized I think I yelled at the computer. Sorry. Which then means we have our positive over here. Okay? That could be secondary versus primary. It's better than secondary versus primary because what is special about that positive? It has resonance, which means we have two potential options that could come out of this. We have the system where we have our pi bond move to the middle, and now our positive charge out here, or we have the original structure. So both of those are existing forms. They are not technically independent structures because they're resonance. They're happening at the same time. Okay? So now what can happen? What else is floating around?
Bromide.
We also have the bromide floating around with its negative charge. And what could it go through and do? Attach to the positive carbocation. Which carbocation?
With the most stable one.
Okay. If it goes to the most stable one, is that left or right? Left. Okay. So we'd go there. We'll call this our most stable carbocation. Okay. And our resulting structure, where I'm zoomed, I can't see very well, gives me the bromide, yeah? Okay. And it's the most stable, so the other product shouldn't form, but you know, for giggles, why not? All right? So we get those two products. Okay. Now the fun question. You ready? Which one's more stable?
The top one's. Oh, wait.
That's a hard question. No, they're all neutral. We can't tell. You can tell what's the most reactive thing in both those structures.
The pi bond.
Why the pi bond?
Because there's electrons there. It does things.
The bromide also has electrons.
Well, yeah, but it'll be a partial positive, partial negative charge.
The bromide's attached via a sigma bond. The pi bond is p orbitals. Those should be higher in energy. The primary thing that's trying to drive the energy of these two materials is probably the pi bond. And we look at that. Which of those two pi bonds is more stable? Our quote-unquote green structure or our purple structure?
I see.
The purple. Why? More substitute. Everybody good with that? Okay, so let's backtrack me deleting everything. So what we decided is we'll add some more information, is that the purple one is the most stable. Right? But if we rewind like maybe 5 minutes now, I've got it in black up there, but we'll put it in green. We said the most stable was the secondary carbocation, right?
Well, that's just the most stable. I don't want to call it intermediate.
Oh,
It is?
it is actually an intermediate. Okay? We said the most stable was the green one. That produced the green product. And yet the green product is
Less stable.
not the most stable. What the hell? Why is most stable different? Why is the most stable different through the course of the reaction? In one case, we said the green was the most stable. In the other case, we said the purple was the most stable. kind of gets to it. When we said the green was the most stable, where were we looking? Carbocation. Nope. Follow it up. There's another word. The carbocation begins with an I. Intermediate was the most stable. How about the purple one?
It was a less stable intermediate.
Where's the purple one referencing? Are we talking about?
Most stable.
It's the product. We're looking at different stages through the chemical reaction. That's why things are moving around. Okay? So I can't go through and say, well, I'm the most stable right now, okay, standing on this floor, but then if you teleport me outside to this exact level outside the building and say, are you the most stable now? I'm going to be screaming bloody murder. No, I'm not. You're in an entirely different environment. That's going to change how you're referencing stability. Okay? This is the point of kinetic and thermodynamic. When we're looking at thermodynamic, it's just the raw energy of the products. So typically thermodynamic is easier to call out because all you've got to do is predict the products. Once you look at the products, you can say, well, that one's thermodynamic because I have the more substituted pi bond. So that makes that bottom one my thermo product. What would make the green one my kinetic product?
It's lesser activation.
It's lesser activation energy when we're looking at going from the intermediate to the product. So you're looking at very different stages of the life cycle of your chemical reaction. Kind of, sort of? Okay. If you understand the mechanism really well, it's calling it easy is a really bad, it's not easy, it's not trivial, it's not obvious. If you understand the mechanism, you can make reference to the kinetic easier. I don't know what word to describe. If you understand the mechanism, you can look for the kinetic. You can understand, maybe derive the kinetic relatively well. Okay? The product can be a little bit more challenging, okay, depending on your perspective. The product for me was always more challenging because when I looked at those two products, I was like, well, they're both neutral. They have the same energy. That's where I started. That was my baseline. So I could never figure out the thermodynamic until I started teaching OChem again, and we went through that stuff in OChem 1 where we talked about the stability of pi bonds. And I went, oh, I can look at the stability of the pi bond to explain which one's the thermodynamic. Okay? And for me, because everything I did was mechanism driven, I could look at the stability of the carbocation. There I know something is reactive because it's charged. I could find that chemistry quicker, which is fun because that's the kinetic. Quicker, kinetic. Kind of, sort of? So what we're trying to think through and move through here is recognize what those differences are and then be able to label these things out. So can I delete everything? Because that was kind of our thought process through it. If we go through and look at our products, this will be our thermodynamic product because we have the more substituted pi bond. The other one, okay, will end up being our kinetic, but not because the other one was thermodynamic. Why do I know that one is my kinetic product?
Less activation energy.
Why do I know it's a lower activation energy?
More stable intermediate.
What I would have to recognize is my path through. And of course, we had these swapped. Okay? The better way to draw those would have been flipping them. I already forgot what the structure looked like. Oh my God, I'm such an idiot. Okay. So if we were to look at our energy diagram, the kinetic, this is a lower activation barrier than the other one. This one is a higher activation barrier, taking us to the thermodynamic. Drawing out the energy diagram, it does get tricky depending on how you want to set this up. The way it's described in the videos is technically wrong. Let's do this one. This one's red for thermo. Our reactants start at the exact same place. So blue and red. There we go, purple. Okay. We could draw out our products. Our thermodynamic needs to be the lowest in energy. Our red. Our kinetic needs to be higher in energy than that. Okay. The next part has to do with the intermediate. So we've got reactant, intermediate, product. That's an I for the record. The intermediate should be higher in energy than our reactant because it's charged. Okay. And if we were to draw out our curve, we're looking at something like this. And if we look at our other one, the intermediate is slightly higher in energy, we get something like that. And what we're talking about is the activation barrier being different for each of those. Why is this diagram misleading? It's a really hard question for the record. What is the relationship between our intermediates?
They're resonance structures.
Which means
They're both happening at the same time.
they're one and the same. Does my energy diagram show them being one and the same? No. So really what should happen is something more along these lines. The blue one has an activation energy that goes there. The red one has an activation energy that goes there. They're both going to the exact same point, but the blue one has a lower activation barrier because of generating the resonance form that's lower in energy. Kind of, sort of. When it comes to the exam, when I've asked this question, I gave credit for both this, which is more correct, and the separated out resonance forms for intermediates. Okay, because they're both getting at the right idea. One missed a pretty admittedly large nuance that I should never have goofed on. But I did. Make sense? Okay. Labels within it. We already talked through some of these. We've got a transition state, which you can get away with a double dagger. I'm fine with that. You've got kinetic product and thermodynamic product. Those labels were already there, but we should technically drop them down here. K and T is fine. Activation energy. These were our activation energy arrows. And that was the last one on it. And technically it says only the last step will be graded, and that's because I'm trying to avoid that screw up that I made. Because you're starting at the same point. Kind of, sort of? Okay. With that,